So today we are going to cover the different topologies of multi-agent system. Okay. So this is the bird's eye view of today's class. So we will start with reality check in production. When a multi-agent system is deployed, then what are the factors which are advantageous and what are the attributes which are not advantageous? And many times many people have written multi-agent, uh, different types of books on multi-agents. So many things look very nice in books. For example, autonomy, decentralization, debate agents. We will build very fancy things, but everything comes with a cost, and that cost is decided. It can be perceived only when you actually build that multi-agent system. So we will start with that, doing a reality check from production, and then we will see what are different types of agent topologies. Right? There is multi-agent architecture, there is single agent architecture. In single agent, we have been doing, as in the generative AI course, we have created a movie recommendation system, and we have created a chatbot multi-turn conversation AI model. We have created a what was that summarization model, right? So all these are single agent architecture, single agent systems. So today we will look at what is multi-agent architecture. And there are various scenarios in which we use multi-agent architecture. For example, rack, and for example, chain of thought. In chain of thought, first for example, ETL pipeline. First we extract the data from from some binary, from some blob, and then we transform the data, we do some post processing, then we load the data into the database. So there are three steps here. This is called chain of thought. For example, if you want to convert a YouTube video into a blog, so first you will transcribe the video, right? Then there will be some post processing to bring structure, uh, transform it into a page format, some paragraphs, segregation of contexts, right? When the video changes the context. So once that is done, then there will be a third agent which will do the HTML styling, and there will be a fourth agent which will upload the styling and the um, segmented paragraphs together into a web page. So there are four agents in this system, and how this multi-agent architecture works, we will take a look into that. What are So there are three types of multi-agent architectures. One is vertical hierarchical, second is horizontal, third is hybrid. So in this case, when you are transforming a video into a blog, first there is a transcriber agent, then there is a transcriptor, this web development agent which lays down the JavaScript and HTML, CSS. And then there is a third agent which takes output from the transcriber, and it segregates the context. Suppose there are five different contexts used in the same video. So it will divide the entire content of the video into five paragraphs. And there will be a fourth agent which will combine the output of second and third agent, which is the styling, and the five paragraphs which are generated by the third agent, and combine them both and generate a HTML web page. So here we can see, like, this is like a hierarchy. This is a vertical hierarchy. The fourth agent is managing the second and third agent, and the output of first agent is fed to second agent also and third agent also. So like this, there is a vertical hierarchy going on. So this is like a vertical architecture. Second type of multi-agent architecture is a horizontal peer-to-peer architecture. So here agents compete for autonomy. For example, there is a master-slave architecture where there are 10 slaves. So suppose the master has to return output of a bucket, and it sends the request to three slaves, and all the three slaves die. So now rest of the seven slaves, to which slave the request should go, the seven slaves will compete from with each other. So this is how agents will compete, and there is a peer-to-peer communication going on. So there are many distributed algorithms like Paxos where this thing happens, Byzantine algorithm, where after their mutual agreement they decide their leader, just like we do election, right? There is a democracy, people decide and the majority wins. So similarly, this Paxos, Byzantine, in operating systems also they do the similar. There is a peer-to-peer competition, conversation agreement going on between different agents, and there is no hierarchy. For example, in a company, right? There is a manager, there is a program manager, there is a tech lead, and then under the tech lead there are senior engineers and junior engineers. So, for example, there are five junior engineers who are given a project. They will work on that project. So they will do a lot of communication within them. So that is peer to peer horizontal. But now suppose they are blocked on something. So they will ask the TL. So TL, or there is a conflict whether I should do or he should do. There is some fighting going on. So that will be resolved with the help of the TL. So that is in general vertical architecture, where the manager will supervise the communication between the two agents. They are not fully mature, and in case of horizontal, they are fully mature, and their program, their code, they are so programmed that they are mature enough to converse with each other. And finally, there is a hybrid level, right? In this hackathon model, also, there is a hybrid communication going on. First of all, they try to converse within each other, and if everything is going fine, they are productive, the output is driven, then it is good. They will remain on the horizontal pair. But if again there is a deadlock, there is a conflict, there is a blockade in the project, they are not able to proceed, then they will approach the higher authority, which again will simulate the vertical architecture. So there is a combination of vertical and horizontal going on. So this is like a hybrid multi-agent. And then there are function topologies. There are three function topologies: reason and act, plan and solve, human in the loop. So reason and act means the agent, different agents will do different things, and then there will be an orchestrator or decision agent which will reason the output of different agents, and depending on that it will take a decision using its intelligence, and corresponding to that intelligence it will act. So similarly, plan and solve. Suppose there is a project. Suppose there is a statement that there will be a election 1 year after. You have to plan for it. You have to and solve how you can win this election. So we will make a plan. We'll make a vision for next 1 year. Okay, we will. This will be our manifesto. This will be this much amount of investment we'll make. This much amount of food we'll distribute. This much amount of blankets we'll distribute. This much amount of monetary compensation we'll give to the below poverty line people, and these many people will be basically needed. This much money will be needed. This many resources will be needed to run the manifesto. So all this planning will be done. At which month, which step will be done, so that finally we are sure that there is one party which is winning, which is our party. The manifesto is successful. We are able to convince people that they will give vote to us. So there is a plan, and then finally we solve it, and then we achieve the result. Okay, so all this is done by topologies of agents. Different agents are doing different things. There will be some money agent, there will be some food agent, there will be some resource agent, there will be some time planning agent, there will be some troubleshooting agent. So all these four agents will interact with each other. Am I in the right class? One second. Okay, I think I'm in the right class. Okay. Okay. So, anyways, plan and solve also has multiple agents. And then there is a human in the loop. For example, you raised an issue, and then another agent, it came across the issue and it tries to troubleshoot the issue. It tried to figure out the solution in multiple steps, and finally it proposed the solution, end to end troubleshooting solution. What do you say? The root cause and the root fix, and then it requires a approval from a human. So there is a human in the loop. There are troubleshooting agents, there are planning agents, but final solution, in order to implement it, we will require the approval of the human. So that is a third function topology. All three topologies can also act among themselves. Okay, next what we will do once we take a look at these, we will go deeper into a use case. For example, if you are building a AI customer support system and you are building it using a hierarchical manager worker model. So, what are the challenges this architecture will face, and what fixes we can do to fix those challenges, to remove those challenges, or to mitigate those challenges, and how the architecture will change by those fixes. All that, how the architecture will evolve, and what is the changed architecture. Everything we will discuss in the use case one, the AI customer support, which is a relatively straightforward design. In the second use case, what we will do is we will have research and decision support agents. So suppose I said ki we have to collaborate with this company and determine the profit which we will make after collaboration. Okay, and make a plan, make a strategy whether we will be able to make sufficient profit. So there is no decision to be made, right? Research needs to be done on the strategy which we will adopt with this collaboration. So the entire analysis needs to be done. And then finally, based on that strategy and analysis, we'll take a decision. So we need to design a multi-agent system where different agents will do different things. Okay. One second. Is there anybody? Ah. So different agents will do different things, and it's an open-ended problem, right? So it is not like you have to. Every agent will be giving some yes or no answer or some fixed output. There will be discussion going on the decision, on the strategy output, on the visualization of this flow, which will happen once the collaboration occurs. So all these things will be discussed in use case two. And the final is we will do a guided discussion. What is this? So we will create, just like we discussed these two use cases in detail, we will have another use case where we will see how different agents were coordinating an incident response for a cloud outage. So generally, in companies like Google or Amazon, VMware, outage is very common. We used to call it post-mortem. Whenever there is an outage, we do a root cause analysis, and then if we still one person is not able to figure out the root cause, then it will store the analysis which it has done, and then another person will take a look at it. Or another approach is two persons, they will simultaneously look into the same outage. So they both have different flow of the postmortem. Okay. So once their analysis is done, even after that, if they are not able to arrive at the solution, then they will discuss among each other that this is the probable solution, like that. So which topology we should use in troubleshooting that incident? and how we should coordinate between these two agents. So that is what we will do as a guided discussion. And finally, in the closing, we will discuss what all topologies are, we discussed, and how the topologies evolve as we fix different types of issues. And the basic thing is like all the issues in a multi-agent system are very similar to what we encounter in operating systems and distributed systems. For example, in operating systems, there is a deadlock, right? One process is waiting on a resource of second process, and second process is again waiting for a resource from which is acquired by first process. So there is a deadlock. Because of the deadlock, there will not be any progress. And then in distributed systems, we have many concepts like centralization, decentralization. There is a central load balancer which redirects requests to all the application servers. So that load balancer becomes a single point of failure. So then we need two load balancers because of that. Because if that goes down, the entire system goes down. And in companies like Google, 1 millisecond delay in search latency is equivalent to two SWE jobs. So Google can't afford any downtime. It costs many lot of loss. So we will discuss that right in the hard-won losses, how the architectures are evolving, and how we are, yeah, how using multi-agent system we are solving complicated problems. Yeah, I was saying that distributed. So whatever concepts we learn in distributed systems like fault tolerance, replication, everything will be involved here also in multi-agent system. Inter-process communication, we'll see shared memory using Blackboard. Okay, so this is the bird's eye view. So now let us start with the first topic, which is reality check from production. What are the misconceptions? So generally, multi-agent deployment on production is difficult. You can do a lot of planning. You can write a flow diagram in the book. For example, there can be multiple agents like planner agent, which plans different other agents. There is a research agent uh, which will take input the research papers from Google, and then based on the planning and research, there is a critic agent which will criticize, give some feedback on the plans and research generated by the above two agents. Then there is a tooling agent. Based on the output of other agents, it will redirect to one of the tools. For example, if Crew AI can be used to transcribe a YouTube, so that transcriber can be a tool, right? This ETL pipeline can also be another tool. So tooling agent means it will just connect with the other tools. For example, RAG, retrieval augmented RAG pipeline is a perfect example of tooling agent because it is an orchestrating framework which just redirects the output of an LLM to another LLM. So it doesn't do anything itself much. It is not an LLM in itself. Then there is a memory agent, which is monitoring the memory, whether it is becoming full or it is shared. If it is a shared memory, then which agent is writing what in that memory. So all that bookkeeping and monitoring is done by this agent. And then there are debate agents arguing with each other. We'll see that also. So in case of debate agents, generally like for especially for the second use case, they will be useful. But there are multiple downsides of debate agents that they can go into infinite loop. They don't arrive at a agreement. They are always giving some subtle subtle perspective, subtle change of dimensions. And so that's the reason that the conversation goes on happening and there is no consensus coming. So we have to tune these agents and figure out that at what point this debate agent we have to conclude. So that's why human intervention is required. And deployment is always difficult because you have to consider multiple things. Context, whether you want to send the same context to all the agents or not. How will the agents communicate to each other? Whether there will be an orchestrator or whether you have to give freedom to them to communicate with each of them freely. So like this, there are multiple challenges here, and ultimately, when you deploy this model, then latency might be an issue. For example, if there is a monolith, then there will not be any latency issue. As soon as you take out a microservice, you have to hit. Yeah, it's no more on the same system, right? System calls are different on different systems. Then you have to make an API call to the other microservice, so the latency increase. If we are creating a new microservice or deploying a portion of the code, then the cost will also increase because you have to install new RAM, you have to install new disk. So cost is increased. Predictability also decreases because what if the microservice goes down? Previously, that code was in a monolith. We knew whether the monolith is on or not, that code is working or not. We can put debug statements. Debugging is also difficult, right? Will not be suppose the signal goes out between the monolith and the microservice. So these are different cases, different challenges which we face in a microservice architecture or multi-agent deployment. Predictability reduces, debugging becomes difficult. Suppose it's a multi-threading application, multi-process application, and lack of control also. Once you have segregated the code into a separate microservice, then if there is very less control, right? You have to do a lot of things. You have to make a monitoring system. If that microservice goes down, there should be alert which should be sent to you so that immediately you can bring it up, or you have to create a replica of that microservice. So multiple things we have to take care in the distributed system. Okay. So that's why we do decentralization. What is decentralization? Can anybody tell what is decentralization in a distributed system? Yeah, Abhishek or Meena. So decentralization means that there is not a single coordinator. So generally in all distributed systems there is a single coordinator. And why is that coordinator needed? Because it has to make the conversation reach at a consensus, at a conclusion. So suppose there is a deadlock going on, infinite loop going on between two agents. So the coordinator will detect that loop, will detect that conflict between the two agents, and it will take some action. So that's why some sort of centralization is needed. If you completely decentralize among those agents, then it becomes a problem. It becomes you have less control. Yeah, and even the retry logic becomes unpredictable. Tool outputs conflict. Agents don't share consistent context. Yeah, so context, it's very difficult to maintain the same context across two different masters, right? So decentralization means you will have multiple masters. 10 masters are there, and each master is dealing with a group of slaves. So centralization is also there, but decentralization is also there. Yeah. So there is a central router which is added, which will decide which slave to choose, right? If decentralization is there. State manager also needs to be added if decentralization happens. Message validator, whether it has reached correctly or not. And failure control also we need to do. So the system becomes more complicated if we decentralize it. And there is no surety of success. There is no surety that the algorithm will run successfully, the distributed protocol will be executed successfully. So that's why there should be some intervention of a common master, of a common decentralized master. Okay. So the slowly when you start supervising, start monitoring these tools, then you figure out that the orchestration is needed anyways. And that's why decentralization is very difficult. It looks, by the word, it looks very beautiful because as soon as you decentralize, you can handle 1000 RPS, 10,000 RPS, but actually you lose control. And having control is very important in avoiding production issues, production debug, production postmortems. Okay. Okay. So we are discussing about the misconceptions till now: autonomy, decentralization, and debate agents. Debate agents also we have discussed that if there is a like conflict in agreement, right? You can just quickly see what is debate agent. Yeah, you can see. So basically, ideally, what should happen is they should converse with each other, and there should be a consensus. There should be a conclusive agreement. But what actually happens in production is that sometimes they arrive at the wrong conclusion if there is an agreement. So and if there are multi-turn conversations going on, then they increase the token usage. So right, like this context window, token parameters, everything is. So if the context window is more, then you have to employ more parameters, and then the token length becomes lesser. Token usage becomes more. So everything comes with a cost. No free lunch theorem is there one. Okay. So yeah. So this is the basically overall debate agents. They don't magically improve quality, and many industries say that they are just expensive self-talk. They agree on confidently wrong answers. They don't actually validate against ground truth. So they forget the facts. They forget validating through a higher authority, through the ground truths. Yeah, and they are not doing any. They are not supporting their result with a external retrieval like RAG, just like we discussed pipeline automation, right? If we do a multi-agent system to create and deploy a pipeline, then you can retrieve an existing deployed and created pipeline and compare the output generated by the multi-agent system by that standard benchmark. So nothing like that can be done within two agents, and verification logic is also not there, and there is nobody to critique. Right, somebody should critique both of them, then only they can be taken into right direction. So it's very important to take them into the right direction. So guidance from a higher authority is important here. And then there is no evaluation metrics also. Only evaluation metrics might be that how much time are they taking to arrive at a consensus. So it just becomes expensive talk. Expensive self talk only. Self talk means you are not discussing with a higher authority. So if you are going into your own patterns, if you are going into your own problems, then nobody will be there to help you. So these are the three major problems basically: autonomy, decentralization, debate agents. On paper, in books, you can say that all these three are there, so it's nice. Yeah, if you have autonomy, decentralization, and debate agents, it looks nice in the textbook. But when you start creating code for it or start deploying on production, then you face various issues. It might look nice in terms of scalability, but it is hard to run them on production. We have discussed now all three. Okay, why and what all does it spoil and makes difficult? It increases the latency, it increases the cost, decreases the control of the system, and observability becomes difficult. For example, when I was in Reliance Jio, we created a S3 system from scratch using distributed file system Ceph. So there is one feature which S3 gives is multi-part upload. So in multi-part upload, what happens is, suppose there is a 10 GB file. That 10 GB file is uploaded in chunks of 1 GB. And every GB after being uploaded, it gives a MD5 hash. And then we receive 5 such MD5 hashes. And then we basically, once we receive all the MD5 hashes of the 5 multiparts, then we create a master hash and then send the response out to the user that your multipart upload is successful. And we do the multipart upload in parallel of all these multiparts. So somehow we were facing a bug in the operating system of our file system in doing multipart upload. So it was very difficult to debug this bug because we cannot see that what is happening on the file system for each multipart. We needed very strong logging system, monitoring, observability systems, but it was not easy to figure out what is happening. So it is like merge sort. Okay, so observability also is difficult. So next misconception is that if you keep on adding agents, then you have more smarter system, right? If you have it, but the reality is that the more agents are there, the latency will increase more. The tokens which are required for the entire multi-agent LLM will increase. Failure points will increase. If some one agent goes down, then there is a break of the flow. Entire system can fall down if there is no proper reconciliation. And state number of states will also increase because everything needs to be replicated. Everything has to be. If somebody goes down, then it has to be restarted. And there can be read write issues if things are happening in parallel. Then we have to make sure that the data is not corrupted. So all these state management also needs to be done. The more agent we increase, yeah. But the real smartness of systems increases when the prompts are good, when the retrieval are good. If we are retrieving a existing pipeline from the database and we are comparing our output with that, so how good is the benchmark? That determines the smartness of the system. Better context management, how we can communicate the same context through all the agents. Suppose it becomes difficult as the topology becomes more complicated, the context management becomes more difficult. But if it is managed nicely, then it is easier to to maintain the smartness of the system. And evaluation loops after some, for example, if you give 100 requests on a multi-agent system, so now you should see what happened to those 100 requests, whether they were served to the user, whether the users are happy with the response of that 100 requests. So all this evaluation is done and understood whether everything is happening correctly. So these are more important rather than just keep on adding agents. If you are adding an agent, then you have to calculate all this. You have to see how to give a smarter prompt. You have to retrieve from a benchmark and compare the output. Yeah, you have to see whether the context is managed cleanly from agent to agent, and then the data is reaching the user. So like this. Okay. Yeah. And another misconception is that there should be a free debate between agents. Right? These days also like feminism is there. Why not they do everything independently? Independently we should not do anything actually. We should consult. We should do it together as a team. We should make a pair of we should make some pairs, decide among themselves whatever resolve or whatever problems are there at their level, and whatever remains, that they should take to the next level. So free reasoning is allowed to a certain extent. Beyond that, there will be some rules imposed by the authorities. So free reasoning causes tool overuse, repeated steps. Yeah, you don't know whether the dialogue will summarize after 10 steps, 10 epochs or not. You don't know whether basically the agreement or the consensus reached is the right consensus or not. You don't know whether you are abiding by the ground truths. We also read about this constitutional AI, right, in our generative AI workshop. So there is a constitution, there is a set of rules which the AI system has to follow. So we don't know if they are doing freely debate whether they are following that set of rules mentioned in the constitution or not. And inconsistent output can be random, which have no meaning. So there has to be some control, some supervision, some monitoring, some intelligence which needs to be induced from the top, from the authorities. And based on that intelligence, there should be some degree of freedom to them to decide within that domain. That's why we had, you remember, we studied Minstrel. Minstrel is a mixture of experts. So there was a router, and a router used to take in a request and then redirect it to the particular mixture, particular expert. So based on the parsing of the input request, it decides which expert it should send to. Right? You remember, right? This one. Yeah, this one. So mixture of experts. There is a router which parses the input request and it decides that to which domain that particular request belongs to, and it parses sends that request to that expert. For example, if the input prompt is what is 1 plus 1, then it will do some parsing, it will do some tokenization, and it will figure out that it should be sent to a numbers expert. Okay, so this we saw in our previous. Okay, one second. Okay, so agent should not reason freely actually. Yeah, they assume autonomy is always good. Each agent independently decides what to do. So there are some pros and cons to everything. So instead of three API calls, you get 40 API calls if you are given autonomy to each agent. So that's why you need hard stop conditions that okay, there is a threshold of debate. You can at most have five interactions. You can at most take to complete those five interactions. You can at most do 20 API calls because after 20 API calls, we will lose our memory budget. So there should be some within the boundary we have to be free. Okay. Yeah. What really matters is latency. So in a real service to service architecture, 2 3 seconds feels slow, and 5 second means UX is gone. So every extra agent actually it calls a new model. There is a new network round trip. There is a new tool invocation. So the latency goes for a toss. Similarly, cost also goes for a toss. Every agent call is using around 3 to 10,000 tokens, and there is a debate going on. So there are double number of tokens. Reflection has triple. First you transmit the meaning and then you reflect. Tool calls, embedding is also there, completion is also there. So all the different tools you will be calling for embedding for completion, right? So those also require cost. And then every user which is doing this cycle end to end. So it results in a high bill per month bill. So in production, we should Yeah, the real scenario comes into picture when we deploy this on production, and we should cap our budget. Suppose it goes beyond 20 lakhs in next 6 months, then we will not. Then we will call it out. We will not allow more users to hit requests, or we trim the context window also. As the context window increases, the number of tokens and parameters required for the LLM increases. So we trim the context. At a time, we are able to look only at these five tokens. That is the context. And then we can cache. We can use some cache like MongoDB, Elastic Cache, EC2, so that cost is reduced, latency cost, and memory cost also. And wherever possible, decrease the number of roles. The more the roles, the more the cost increases. Okay. So production system. Yeah, let's take a 2 minute break. I'll be back in 1 minute. You can also drink water or something. Till that time, what you can do is you can look at this diagram, and you have to tell that which one is horizontal multi-agent system and which one is vertical multi-agent. Multi-agent and which one is horizontal. Yeah, welcome back. Okay. So can you tell which one is the vertical multi-agent, which one is horizontal? In the first one, orchestrator is managing different workers. In the second one, the classifier is picking the pipeline, one of the pipeline. This is also called router solver. And the third one, there is a hierarchy. And in the fourth one, there is a multiple. Yeah, it is not only forward, it can be a backward communication also. So which one? I think vertical is involved in every topology, but in only one topology there is a chance of vertical communication also, horizontal communication also. Can you guess which one is that? Am I audible? So only in this topology we can see some horizontal communication. Here that communication is vertical. Here also it is going this side. Here also it is going this side. Here it is going this side also, but it is bidirectional. And within the same level also there is communication. Node B can converse with node E can converse with node F also. This is called decentralized peer-to-peer network. This is input directs to specific pipelines. This is central node delegates tasks to subnodes. This is layered command structure. So this is peer-to-peer. But there are always like challenges with peer-to-peer. You need constant supervision that they are going in the right direction. So that's why generally there is a master, there is a manager, coordinator. Okay. Yeah. So in theory, it is assumed that autonomy is always good, but in reality, autonomy creates loops between agents. Sometimes there is a different agent starts hallucinating the task. So task is something else, and they produce something else. The task itself got changed. Agents call tools unnecessarily. So there can be a vast increase of memory usage because of this. And I've seen this while working on Amazon and Google databases like DynamoDB, RDS, S3. So many multi-programming, multi-threading codes were very, very difficult to debug. You get 40 API calls for something that needed three. Yeah, I've discussed this. But what is really good in a real multi-agent system is that there is one orchestrator which manages all the different agents. It manages state, it enforces budgets, it routes the task to the right agent, right? That that agent can be a expert also. It controls flow, and there are tool bound specialists. As we discussed, that there is an expert for different domains. So, for example, there is a mathematical expert, there is a vocabulary expert, there is a geography expert. So, tool bound specialists help us to solve problems easily. And the number of layers, hidden layers required can decrease to a large extent because of it. The context, the number of parameters of the computation also is decreased of training that model. And then it can have some hard stop conditions: maximum epoch steps, maximum tokens, maximum retries, timeout guards. that how many tokens it can take in a context window, right? That is the context window, or maximum steps it can communicate between two agents. So if there are hard stop conditions, then basically multi-agent system is good. If they are not, then that can lead to overhogging of CPU memory or any unpredicted thing. And observability is also a silent killer. So here, just- and retrieval is greater than debate. Matlab, we are arguing less, we are discussing less, and we are having the benchmark with us. So we try to validate our answers with that benchmark. Okay. So this is called RAT plus validation. That is greater than agent arguing with themselves. And observability is the first thing. Tracing, logging, cost tracking, replayability. So if you are able to have these functionalities, then it is very easy to monitor any multi-agent system, and you will be able to control it. Control it means at least you will be able to track it. If there is an error procured by a user, you can debug it, you can fix it. So there are multiple logging infrastructures. In Reliance Jio, we were able to immediately debug the request which we are firing. In VMware, we were using something known as Kibana to fetch the log. We had to explicitly go to a system and then type the error string, and then it will give you some uh, log files, and then you have to segregate. In Google also, there are different tools. There are 4 or 5 stacks which you have to go through. So the logging becomes more and more difficult actually as I proceeded from these companies. First of all, I thought whenever for a developer, immediately as soon as you start writing code and you test the code, immediately first thing you look at is the log. You'll put some print statements. You will see whether those print statements are in the output or not. And if there is any issue, only source of debugging that issue is the log. What is the error? Then at which line is that error happening? So to see the line, at least we should have log in one step itself. But I was very much pained by the logs provided by VMware and Google. We had to dig in 10 steps to figure out the line of the error. Yeah. So it's difficult. Managing logs are challenging at every place. Okay. So now these are the different topologies. So one of the topology is single agent architecture, which I mentioned you right. Recommendation system, summarizer, chat bot, code generative bot. So this is a single autonomous agent which is equipped with tools, memory, and reasoning capabilities to handle a task from start to finish. Ideal for focused, straightforward tasks like personalized research or simple customer support chat. Multi-agent architectures means you are breaking down the larger problem into smaller problems. It has multiple specialized agents who collaborate, delegate tasks to each other to solve complex multi-domain problems. And there are three types of such multi-agent architectures: vertical, horizontal, and hybrid. Vertical means there is a hierarchy between manager and the slave and the master. So the manager breaks down the high-level goals and delegates specific subtasks to subordinate specific agents. And it is good for compliance-heavy tasks like loan processing. For example, suppose you apply for a loan in college. Then first of all, you have to check the identity of the person. Then second agent will check what is the salary that person is earning. Third agent will check how many liability it has, that person has, how much assets he has. Then the fourth agent, he basically tries to create a decision based on the output of the first three agents. So there are different worker agents. Okay. So this is called vertical architecture. Master agent is the person who is aggregating the response of all the other three agents in loan processing. Second is horizontal architecture, where agents work as equals, communicating freely to solve problems. So best for creative dynamic workflows where roles might shift. Yeah, creativity can lead to destruction also. It can lead to very, very random outputs which are way away from the truth, ground truth, the benchmark. So they should be guided, they should be under some consultation guidance. And hybrid architecture, that's why, is considered best, which is having both combination of vertical and horizontal. The challenge is with vertical architecture is that the master architecture or the what is say yeah or the coordinator that becomes a single point of failure. That is the challenge there. So we are not able to scale properly that thing. Apart from that, everything is good. In horizontal, scaling is very good, but there is a high probability of not able to arrive at the right conclusion. So that is there. And then there are functional topologies. We have already discussed this. Okay, so this is an example of a vertical architecture. Start, then branch, then we create three agents. All the three agents we give some task. First agent to summarize, second agent to translate, third agent to understand the sentiment. And then we learned, right, the embedding, which is generated from a token using word-to-vec algorithm that contains everything, the sentiment, and what are the entities, what is the intent of the user. All things are captured in that embedding. So this diagram also is doing something similar. It is trying to produce a vector which contains all these three information. And this is also an example of vertical agent where supervisor agent is trying to answer a question from a user. Every agent, one agent to agent three, will give a response, and then which will be returned back to the supervisor, which will intelligently compile the response from these three responses. Okay. So let us go through the first use case, which is the AI customer support. So there is a customer support app which actually has lot of people interacting with it. They are creating tickets, they're creating bugs. In corporate, there is something known as sprint. For every sprint, we create 20 bugs, and there might be stories, epics, which might be projects in themselves. So there are a lot of bugs, and when you deploy a feature, every team has its own bugganizer ID. So there is a very high ticket volume in a vertical like Amazon, AWS, or Google Search. And then within that customer support, there can be three different domains. Okay. First is billing. It is trying to calculate the bill for the user, how much resources the user is using, what all clusters are deployed for its use. Second is technical, right? It is able to troubleshoot if there is an issue in any of the nodes. Then finally policy, whether the user is not violating the policy or not. And then there are SLA and escalation requirements. Suppose the minimum SLA is not met or the problem is not being solved by the customer support, then it has to be escalated to a senior manager. And only SLA means only 5,000 requests per second can be entertained. After that, we have to think about something. So this is our over like requirements of the customer support we want to build, and the features which it will support, and the basic idea of different agents which we can create for this customer support, yeah, entity. So the most probable architecture which we will employ is a hierarchical manager worker model, which is a vertical model. Okay. And in this, you will have three types of agents. One is orchestrator, one is domain agents, and one is escalation logic. So domain agents can be three. One is billing domain, second is technical domain, third is policy domain. So this is how the diagram will look like for customer support. Customer sends the web, the application. So it is interacting with the customer support application through an email or through a portal, uh, website portal. And then once the request of the customer reaches, it goes through an API gateway, chat interface layer, and then that API gateway parses the request and it translates it into proper, which can be sent to the database. So then the parse request is sent to the orchestrator, which tries to figure out the intent behind that request, and it tries to figure out the context and the domain. Suppose the input query belongs to the punctuation expert. Then you reroute your query to punctuation expert. SLA tracking, right? So orchestrate will figure out whether till now how many requests have come in last 1 second. If it is breaching one of the SLA, then it will reject them. So it acts like a agent also, managing routing, filtering, all the agents functions orchestrator is doing. So it redirects the request to two agents, billing agent and technical agent. So billing agent, what it does is it scans all the invoices. It takes care of the refund if any required, and it tracks the life cycle of any user, the billing cycle of any user. What is the payment status? How much he has paid already? What has been billed till now in this month? What kind of plans we can float? What kind of recommendations we can give? All these things, billing agent will take care of. Second is technical agent, which generally the main purpose of technical agent is troubleshooting. Suppose if some person is having some technical issue, the AWS cloud has gone down, or there is an error in the cluster. So all this comes under technical agent, system diagnostics and troubleshooting. Yeah, there are many challenges to this architecture also. So then even billing agent and technical agent, they are feeding their output to policy compliance agent, which is the another domain worker, which will figure out whether all the constitutional rules are met. And then if it is met, then logic layer is the last, which will give confidential threshold, sentimental detection, SLA breach detection, compliance flag, and human supporter. So, so based on the confidence which these agents can show on this ticket, it can be decided whether it needs to be transferred to the higher management or not. Okay. So there are multiple places at which this entire design can give us challenges. First is the orchestrator. It can give bottlenecks because it is a single point of failure. Second is context loss between agents. Since different agents will be coordinating with each other, for example, billing agent goes to orchestrator and then orchestrator calls technical agent. So there can be a probability of losing context. The common context is not maintained anywhere. And cost spikes during peak load because the orchestrator is also managing the SLA. So peak load means there will be some outages. Some requests will cannot be served. So the spike costs are increased. The orchestrator has to done everything. It will track the context of all the agents, all escalation decisions, all validation, all routing, all requests. So this creates a single high traffic checkpoint. Yeah. So let's do some programming now. Okay. Because we have seen it, the we can see the evolution of this agent also. But let's write a lang chain program. First of all, we can write a like. Sorry. So we'll write a lang chain program. First we will install lang chain. So this is done. Then we can import LangChain library.